Hi, I'm Rohit Sahu. I will be presenting the paper Distributed Neural Network Inference on Severely Resource-Constrained Edge Devices. Pervasive edge intelligence promises a huge number of smart nodes deployed everywhere that could revolutionize society from agriculture to manufacturing to smart infrastructure and beyond. The nodes will be deployed in hard-to-access locations like farms and villages and need to be continuously monitor and analyze data at the source and make intelligent and often critical decisions demanding high capability machine learning. However, the nodes must process data without sending it back to the cloud to avoid unreliable and costly communication. Additionally, for ubiquitous deployment, they need to be low cost and low maintenance. For long lifetime in hard to access locations, nodes may use small batteries and energy harvesting coupled with low cost. This means that such node will employ ultra low power processors. Such processors are severely resource constrained. For example, we show some of the ultra low power processors submitted to ULP mark. We can see that the memories and processing capabilities are under a few hundreds of kbs and few tens of megahertz. This is unfortunately fundamentally at odds with the memory and computation requirements of many machine learning applications. For example, consider MobileNet, a 28-layer neural network optimized for image classification on mobile devices. For each layer, we show the total memory footprint breakdown into text, which is a code memory model, which is the memory needed to store the raw weights and biases of the network. And finally, tensor arena, which is memory needed to store the intermediate tensors. The black line represents the total memory capacity of the MSP430, which is a commonly used device for battery and energy harvesting sensor nodes. As we can see, even MobileNet, which is designed to work on a mobile device, is still too large to fit for us on a severely resource constrained edge node, such that even most of the layers are too big than a single node. Of course, significant work has attempted to reduce the overall resource consumption of neural network. For example, pruning, quantization, and even reduced input size have been studied. In the figure, we show Pareto optimal top 5 accuracy on y-axis and the total memory requirement for 16 different possible mobile nets on the x-axis. We show different color shaded region that shows the required number of MSP430 nodes that would achieve the shown Pareto optimal accuracy. We can observe that even with a decrease from 90% to 65% of accuracy, we still cannot fit on a single node of MSP430. As a result, it is very critical to distribute inference across multiple edge nodes to enable neural network inference at otherwise infeasible accuracies. So the goal of this work is to distribute high accuracy neural networks across minimum number of severely resource constrained edge nodes. Cover up with Denni statically partition the neural network computation as shown here. Denni takes an input the node constraints such as memory and a baseline trained neural network TensorFlow light graph, and it uses a distribution algorithm to produce a splitting parameter that defines which part of the baseline trained neural network inference, like both model and associated computation, is mapped to different node. A model splitter applies this split to the neural network model, producing unique TensorFlow light model for each node. These models, along with the custom 16-bit implementation of TensorFlow Lite Micro, are compiled using a GCC MSP430 compiler into barebone binaries that are programmed to the appropriate nodes. The key challenge for Denni is determining the best split parameters, that is a distribution algorithm implementation. Since neural network may be too big to fit on a single pervasive node, Denni must consider splitting within a single layer, that is interlayer splitting. Here we show a convolutional layer example. The input is convolved with the weights to produce the output. We can reduce and distribute the tensor arena, that is the memory region of the input plus output, by taking subset of the input volume, as highlighted in red, and computing associated convolution across different nodes. Additionally, we could also reduce and distribute the weights of the model by computing a subset of the original output channels M prime out of M across different nodes. The result is both reduced weights per node and the reduced tensor arena. Given a particular node memory, we can formulate this as an optimization problem that minimizes the number of nodes given the node memory constraint. However, considering adjacent layers together offers further reduction in tensor arena size, since the input to the first layer and the output to the second layer can use the same memory. We call the layers considered together as layer chunks. Here we show two layers, a depth-wise convolution followed by convolution. Uh, Similar to interlayer, here we also place the different subset of the input volume across different nodes. So this reduces the tensor arena shown in red. The tensor arena now is a max of the pairs of highlighted red volume. For example, it is max of t prime 0 plus t prime 1 and t prime 1 plus t prime 2. Although this requires a model ways to be replicated across nodes, it reduces aggregate arena and number of nodes for the initial layers that are significantly dominated by arena memory. In addition, there may be layers that are too big in both arena and the weight memory compared to a node size and may need both cross layer and interlayer splitting to even produce valid partition. We show the general scenario here, which incurs some communication over highlighted in green. We extend this concept to layer chunks of arbitrary number and develop mixed integer nonlinear optimization formulation to minimize the number of nodes. So given this option, how do we partition neural network end to end? So let's consider a general neural network having n layers rising of k convolution and q pooling layers and the rest of fully connected layers. Even if we just consider all possible combination of just convolution layers, the complexity is big of 2 to the power k. Example, for a neural network with 50 layers, this would be like 2 to the power 50 possible layer chunks to consider, which are too many. So instead of trying to consider possible layer chunks, we use a heuristic based approach. Our heuristic-based approach is based on certain observations, such as since the cross-layer model is increasingly replicated across nodes, the per node model size increases with each additional layer in the layer chunk, while per node arena size decreases. However, the tensor arena reduction also diminishes as layers are added to the layer chunk. So model and the tensor arena memory constraints are opposing forces which end up limiting the optimal layer chunk size to a relatively few number of nodes. Therefore, Denny starts at input and iteratively builds layer chunk. Our goal is to find largest layer chunk size that balances these two forces while minimizing the number of nodes. To better understand, let's consider an example. Consider this 5-layer neural network. In the first step, we apply the intra-layer mixed integer nonlinear programming to all of the layers. Now starting at the input, we use our cross-layer mixed integer nonlinear programming to solve for layer chunk 0 and 1. The solution partition requires 6 nodes. Since this is less than the sum of the minimum nodes for layer 0 and layer 1, we add it to the list of the layer chunks and update the previous best node to 6. We solve for the layer chunk 0, 1, and 2. It results in 11 nodes. Since this minimum nodes for the layer chunk is not less than the previous best plus the plus 4, which is the minimum node for layer 2, we terminate our layer chunk and update the previous best as 0. Now again we start forming layer chunk starting with layer 2. As we show here, we solve layer 2, layer 3, layer as a layer chunk minimum, and we have 4 nodes. Since 4 is smaller than minimum for layer 2 plus minimum for layer 3, we add it to the layer chunk and update our previous node best to 4. Now we again use cross layer min-LP to minimize the layer chunk 2, 3, and 4. We found that it needs 8 nodes. Since 8 is still not smaller than the previous best plus the minimum nodes for layer 4, we terminate our layer chunk and update the previous best to 0. And now we would be using layer 4 to start calculating a new layer chunk, and this process goes on till the end of the neural network. This is how we build up and party the successive layer chunk. Let us now consider how this works for a real neural network. So before that, for evaluation, we have used certain benchmarks. So we have used benchmarks for different data types. For example, one does image classification, like mobile nets, and the others like time series and speech classification. So we have neural networks with different depth, convolution, dense operators, model, and arena sizes. Here we show how Denny performed in terms of minimum node for MSP430 with 256 KB memory. On the y-axis, we show the total number of nodes uh, resulted by the partitioning. On the x-axis, our benchmarks. First, we observed that none of the benchmark fits on a single node shown by the gray cross, even if we execute each layer on a single node, as shown in the red. Even that won't work. However, by splitting within each layer, Denny can enable inference on MSP430 for all the neural networks. For neural networks that are not dominated by the weights, Denny can further reduce the number of nodes by 44%. We also show a minimum bound in blue, that is number of nodes assuming total arena. The model size can be uniformly distributed across nodes. This is unachievable bound because we cannot reduce both arenas and model size together. Due to emerging memory technologies and technologies carrying the memory capacity of pervasive node may increase in the future. Consequently, we explored how Denny would scale with increasing node memory sizes. Here we show the estimated min node on the y-axis, and with increasing memory node size on the x-axis. The vertical lines of different color indicate when a single node can fit the whole benchmark. As we can see, Denny continues to provide effective partitioning as the node memory size increases, and eventually the whole neural network tends to fit on a single node. Denny can also provide solution even for a constant node size, although at a steep cost in node number. So now we know that Denny can be effective partitioning neural network across a smaller number of nodes. How does this impact the resulting latency and energy? So to measure the impact on latency and energy, we actually executed each partition binary on MS430 device with 256 KB of memory. The runtime latency and energy were measured using the energy test technology. Since our experiment with numerous partitioning schemes involved up to 100 of nodes, we modeled the network rather than manually setting up the topology of experiment at each time. Experimented with two node system as shown in the image. We connected the CC2640R2F having BLE with the MSP430 by SPI, and we experimented and calculated the latency energy of the communication. Then for each of the partitioning scenarios, we simulated overall inference using fully connected topology. Now let's explore how Denny partitioning impacted the latency and energy of inference. Here we show a normalized latency in log scale. The green bar represents the total latency of a single input inference, including all computation communication latencies. It is normalized to the overall latency when inference is executed on MH430 node with arbitrary large memory. The black line, we consistently observe latency speed up from 1.12x to 8.45x compared to when executing a single node with infinite memory. This is true even though distributing neural networks across nodes increases communication costs due to communication between distributed nodes and recomputation overhead from recomputing intermediate outputs across different cross-layer splits. Then he achieved this latency reduction by exploiting parallelism between layer chunk partition. This becomes more evident as we move towards benchmark that require more nodes. Here we show normalized energy in log scale per benchmark. The dark red bar represents the average per node inference energy compared to the energy cost of a single node with infinite memory. The light pink bar represents the overall inference energy, which is total energy needed for overall distributed inference, which is again normalized by the energy cost of a single node with infinite memory. As we can see that though overall inference energy increased and adverse case by 158% due to extra communication and recomputation. However, the per node energy is reduced by 1.7 to 59.21 times compared to a single node. In conclusion, Denny is a systematic framework that distributes neural network with overall latency and per node energy reduction, and so is promising to enable pervasive intelligence. In future, Denny can be extended to provide dependable inference across energy harvesting, explore techniques such as lightweight dynamical adapting neural network inference, and even can be made richer with benchmarks like RNN and online learning. Thank you for your attention. I look forward to questions.